So I hope most of you were at the yesterday's talk where I gave an introduction of spectral methods and how they can be applied for learning latent variable models. And in particular, we looked at Gaussian mixtures in detail, and we started looking at topic models. And I showed how there's a unified framework of thinking about moments of these distributions, and using these higher order moments, we could obtain the parameters with guarantees. Today we'll take the story forward. We'll see that a range of other latent variable models, with increasing complexity, can still have tractable moments, and there is a unified framework of this tensor method that can be applied to all these different models. And then we'll talk, yesterday I didn't give a detailed analysis of why the tensor method works, right? So today we'll look at some analysis. We'll take an optimization viewpoint. This is non-convex problem, but we'll see that still we can, provide guarantees, and precisely what are the, reasons behind that, right? Because in general, non-convex problems are hard. I mean, you only go to a local optimum in general. But why are tensor-based problems tractable, at least the class we've looked at? So that will be the format of the talk today. So just to remind ourselves, yesterday we looked at unsupervised learning. So this was the challenging setting where during the training time, we don't have access to labels, right? We only have the samples. And in case of, say, Gaussian mixtures, we don't have labels of what components that these samples belong to. So then the question is, how do I learn the model parameters through these tensor methods? So that's where we started, and we saw that there were many challenges when it came to learning latent variable models. The basic statistical challenge was to ask about identifiability questions. When can I hope to identify the parameters? What is the equivalence class of models that can be learned? But usually, like in statistics, you don't worry about the computational complexity. And then, on the other hand, we said that we also want tractable algorithms that are guaranteed to obtain the parameters, meaning they have consistency guarantees, and yet have small computational complexity or low computational complexity. So we wanted like the best of both the worlds, and that's where we were looking at these tensor methods. So now, we can look at the class of probabilistic models, right? So in here, what we want to do is model the relationships between hidden and observed variables. So indeed, we'd like to incorporate a rich class of relationships, and typically, the usual framework is to think of graphical modeling. So you have a graph that models conditional independence relationships between the variables. And one class of models we looked at yesterday was the so-called multiview models. So I call it multiview because you have this hidden variable, and then you have these multiple views of the hidden state, right? I mean, this is also the naive Bayes model, depending on which literature you look at. So this is one way to think about modeling additional statistical constraints, right? So I'm telling you that all these observed variables, x1, x2, so on, are conditionally independent given this hidden variable. So this is additional constraints that I'm imposing on my model. And you can think of much richer class of constraints. There could be hierarchies of variables, there could be loops, and so on. And we'll see today what kinds of statistical constraints we can incorporate and obtain tractable moments that we can solve to obtain the parameters of the model. So, as I said, ours is a moment-based method. We look at higher order moments of these class of models and ask how we can solve this set of equations to obtain the parameters. Right? The traditional framework is to think of maximum likelihood. I mean, indeed, this is the optimal estimator because you'd like to maximize the likelihood of your data, right? The model that maximizes the likelihood of your data. But on the other hand, it is computationally hard to solve the problem in general. And like heuristics such as expectation maximization, it will only converge to a local optimum. So in general, you don't go to the global optimum, and that's why there are no consistency guarantees that you will recover the parameters. And in contrast, what we'll see today is that these tensor methods come with guarantees. You're guaranteed to recover the parameters, and that too with very small amount of computational complexity as well as sample complexity. Right? Because in practice, you only have access to samples. The question is, how many samples do I require to estimate the parameters consistently? And you'd like that to be low as well. And these we'll see are just some polynomial parameters in the ambient dimension, that is the dimension in which you observe the data points, as well as the latent dimension, which in case of Gaussian mixtures was the number of components. So we'll see that they're just some polynomial dependence, and in many cases very low order polynomials. And I won't cover further on this aspect, but there is the Lacombe theory, which is a classical theory in statistics, which says that suppose I start with any square root n consistent estimator, and I do a step of Newton-Raphson method. So I do this optimization after I obtain a consistent estimator, then I can also get statistical efficiency asymptotically. So, I mean, we know that maximum likelihood, right, is asymptotically efficient in terms of its statistical efficiency. And the moment estimator in general is not. So in the sense, you're losing something because you're not getting the most efficient estimator. But then there is this theory that says that after you obtain the moment estimator, if you refine it further, you'll also get statistically the most efficient estimator. Right? And this is one way to do it. I mean, there's also conjectures that if could also run EM after you initialize with this moment estimator, and the hope is it'll land you in the right basin, and then you can refine it to get the the global optimum of the maximum likelihood. And some very recent works have shown that that is indeed the case under some restrictive assumptions, and the hope is we can say it in more general setting. But I won't cover this aspect further, but keep in mind that although the moment estimator may not be optimal statistically, there are ways to refine it further. And so we'll see that yesterday we saw some very simple operations to do tensor decomposition. I'll recall that today again, and these are very simple linear algebraic and multilinear algebraic operations. And tomorrow we'll see how to even implement them and what are some practical issues. Yeah. So as I said, yesterday's talk involved mostly Gaussian mixtures. I started talking about topic models, right? And then we talked about the tensor method, which was to first do this whitening, meaning you convert your unknown set of vectors to an orthogonal system, and then we applied this tensor power method to solve an orthogonal tensor decomposition. And today we'll first start with different latent variable models. So we'll just look at these latent variable models. We'll just write down what the moments are. Typically up to third or fourth order moments. And then we'll see that, in fact, we can reduce it to a very similar form to what we had yesterday. And that's why we can then apply exactly the same technique to solve a much wider class of models. And that's, as I said, a strength of these techniques, that we can have a unified framework for solving a whole range of different latent variable models. So, when you're writing the code, you just need some pre-processing to reduce it to a form which is taken up by the tensor method. And so that's also nice about these techniques. And tomorrow will be about implementation. So let's recall the latent variable models we talked yesterday, right? So there was the Gaussian mixtures and the topic models in the simple case where there is just one topic in each document. And so the Gaussian mixture, we had this notation. I'll try to carry over the same notation even today, that the k was the number of unknown components. And the unknown means were represented by A1 through AK, right? And these were in D dimensions. The observed samples were in D dimensions. And so we had this, that each component would be chosen with some probability, and that's, component I is chosen with probability Wi. And then we have this zero mean spherical noise, right? These are spherical Gaussian mixtures. And we saw that you could also think of topic models in a very similar light. Here now we have k unknown topics. now A1 through AK represent probability vectors. So if I had topic 1, the probability of different words is given by this vector A1. Right? So, and this is a d-dimensional vector where d is the size of the vocabulary. It's a possible set of words that can occur. And we saw that the difference from the Gaussian model is that we have multiple words in the same document. Right? So, and they're all drawn IID from the same conditional distribution. So each document, I fix the topic, and then I draw multiple words. And we saw that for both these models, we could still think of them in a unified linear framework, where I say that the expectation of my sample, given the hidden component, is just a linear function of H. Right? H is my hidden component. A is the is the matrix which is either the set of means or the set of topic vectors. Right? And this is because we encode even this discrete distribution in terms of this one-hot encoding, meaning that each word I represent it with a basis vector in d dimensions. For instance, if I order my vocabulary as apple, orange, and so on, so when apple occurs, I assign it the vector E1, the basis vector for the first direction. Right? And because of that, this is again just like this AH is like a selection process, right? And H is again represented with basis vectors in k-dimensional space because it's one of the k possible components that occur. So with this notation, you can, have both the Gaussian mixture and the topic models. And we'll see a whole range of other models can also would be satisfying this linear viewpoint. And indeed, there are ways to extend it to kernels, but I won't talk about it here. But there are works of mine and others which do that. But so this is the unified, linear model viewpoint. And so what we said was for both these models, we can obtain these second order and third order moments which have a similar form. And we'll see that, these were not directly the raw moments, right? For Gaussian mixtures, if you recall, I estimated the variance. I used the fact what the mean of the entire distribution is. I subtracted some terms out, and then I obtained this form. But in the end, we can compute this from data, right? The empirical statistics of this form. And what we saw was these are just bilinear and trilinear forms of these unknown vectors A1 through AK. So that was the unified viewpoint of both the models. So today I'll be going further and looking at topic models where there can be multiple topics in a document. Right? So these are the so-called admixtures, where now instead of like a pure topic in a document, you have now these mixed topics. Right? So a word could have been generated from any of those possible topics in a document. And so how do we now, it becomes now a richer model. So if you recall yesterday, I said the basic way to think about latent variable models is to think about just clusters or components. Right? So another way to say that is that this hidden variable just takes basis vectors as its realizations. But in general, the hidden variable itself may be continuous. It may have other distributional assumptions. So in that case, we have now a richer class of probabilistic model. Right? And that's how I can want to think about even topic models. Now I can have multiple topics in a document. Right? And the one where we saw yesterday, the single topic model, we saw that these moments M2 and M3 only corresponded to like the co-occurrence of 2 words in a document or 3 words in the document. And we'll see today that we'd have to modify these moments when we have mixture of different topics in a document. And the way to view it is that this latent variable H now represent the proportions of different topics in a document. Right? So now you can think of like a document as like 50% politics, maybe 50% foreign relations. Right? So it may talk about both these topics. So in that case, it's still like part of the simplex, but maybe somewhere interior. Right? And whereas in the single topic model, we know that this latent variable only takes basis vectors as its realizations. So meaning that they're only the only possible realizations are vertices of this simplex, right? Because they correspond to the basis vectors. Whereas in general, now each document could be any point in the simplex. Right? So we are now allowing for this mixed topics in the document. But this part of the model is still the same, because once I fix a certain proportions of topic for a document, that is, I sample one of the points on the simplex, I'm going to generate words according to the linear model I had here. Right? So I'm going to say that the conditional expectation is A times H. Right? So on average, I'm going to take a mixture of the different probability vectors corresponding to different topics. And how I'm going to mix them is given by this proportions vector H. Right? But all the words, again, are conditionally independent given the topic proportions. Right? So here what I'm doing is I'm fixing a point. So one sample is one point here on the simplex. That is one document. And then I'm going to draw multiple words according to that conditional distribution. Right? And each word, since I again have basis vector representation, they are vertices in simplex with d vertices in total. Right? So these are different possible words that occur. Okay, and now this is the graphical model viewpoint. Right? So the graphical model viewpoint is H is now proportion of topics in the document. So in each sample or in each document, I'm going to first fix the realization of H. And now to generate the first word, I'm going to first draw a topic. So Y1 is a topic that's drawn according to this probability vector H. Right? You can think of H as a probability vector. So with probability, say, H1, I draw the topic 1. With probability H2, I draw topic 2, and so on. So I'm going to draw first the topic, and then given the topic, I'm going to draw the word. And that's given by this topic word matrix or this conditional probability table. Right? So I'm going to say this in this matrix A, the ijth entry is given by the probability that the word was I, given that the topic was J. And this is an exchangeable or a bag of words model because the order of words do not matter, because they all have the same conditional distribution once I fix these topics here. Right? So, rather the proportions of topics. So yeah, so this was, we saw yesterday in the kind of the simple case when each document has just one topic, right? All these YIs just collapse to just that given topic, right? So there isn't this kind of additional layer of randomness that I have in a general model, right? So is it clear? In a single topic model, just all these YIs are just equal to the realization of H, which is just one of the basis vectors because I'm only allowing for single topics. But now I have this more randomness because the document itself has multiple topics, and I'm going to first draw these topics, and then I'm going to draw the words. Okay? And so I'd like to now ask how to model this additional randomness. Right? So how do I model the distribution of different topics? And indeed, this distribution should be supported over the simplex, as I said before, because this vector represents a probability distribution, and you can think of it as proportion of different topics in this document. And the most popular topic model is this latent dirichlet allocation, right? So in this case, these topic proportions are drawn from a dirichlet distribution. There is indeed an extensive body of work looking at latent dirichlet allocation. There is a lot of nice properties about the dirichlet distribution, but I just want to give intuitions of why the dirichlet distribution may be a nice one to use as a model for documents. So this is the Dirichlet distribution. Essentially, it has a product form except for normalization. Right? We have to have this normalization because it has to be a probability vector in the end. Right? The entries have to sum up to 1 finally. So we have that constraint, but except for that constraint, it has a product form. And then it has this parameter, these alpha j's. Right? These are called concentration parameters. So what is the intuition of these concentration parameters? Right? So this alpha is now this vector of concentration parameters corresponding to these different dimensions. Right? There are k dimensions. And so, I have this simplex with k vertices, right? This concentration parameter, I'll just think of the sum of them, right? So there are different regimes of it. In fact, like the regime we've already seen is the one where you just send this concentration parameter to 0, right? And you can just maybe think for a bit longer, you will see that this is nothing but the single topic model. So if I send this concentration parameter to 0, I only have probability mass on the vertices of this simplex. On the other hand, like as I keep increasing this parameter, the probability mass moves more towards the center of the simplex, right? But if they're still less than 1, there's still, I guess, more mass, towards the vertices than in the middle. But as you keep increasing this concentration parameter, there's more probability mass towards the center of the simplex. And in the limit, in fact, it degenerates to a single point. So you can see why the term, it's called concentration parameter. Because as you increase this parameter, the probability mass concentrates more towards the center of the simplex. Right? And so the thing is, in the regime when this concentration parameter is quite small, we have sparsity. Right? If you think about a document, and think about all possible topics, right? It's kind of not useful to model a document with all possible topics, right? Most likely, there are only few topics that occur in a document. A document could talk about maybe politics and foreign relations, but most likely not about everything else, maybe not sports, science. Every possible topic in a document is very unlikely to occur. Right? And that's where the Dirichlet distribution can be useful because it can encourage sparsity in the relevant regime of these concentration parameters. So that was an intuition of what the concentration parameter of this Dirichlet distribution means. So now the question is, how can I handle the moments of this Dirichlet model? Right? So we saw that in the single topic model, just looking at co-occurrence of like 2 words in the document and 3 words in the document was enough for me to feed into the tensor method and recover the parameters. But now I have this additional randomness because of this Dirichlet distribution. So how do I handle that? So it turns out that, in fact, you can still reduce it to the same form as before, but you'd have to pre-process the data with some simple tricks. So the idea is earlier, right, I had this M2 as the expectation of x1 cross x2, which is nothing but the probability matrix, the co-occurrence matrix of pair of words in the document. But now you see that depending on this concentration parameter, I'm going to subtract out this term, corresponding to the mean of these observed variables. And similarly, even for the third order moment, it's possible to write out, and there are some more terms that I'm not displaying here. You can see it in the paper for the exact expression. But it turns out that this Dirichlet distribution, exploiting this distributional form we had, we can write out the moments and we can do some very simple pre-processing. And in the end, in expectation, I know that these moments just correspond to bilinear and trilinear forms of the topic probability vectors. So these AIs, right? So these are the conditional probability of words given the topics. So, and you can see that if alpha 0 was just equal to 0, which is the single topic model, all these terms disappear. So we are back to the expression I showed yesterday. So today we just, can do some simple modifications and we can now learn a much richer class of models. Okay, and the other nice thing that this appeared in NIPS, I think last year or the year before. I've lost track. But we showed that to learn these latent Dirichlet allocation, you needed to just have 3 words in the document. Right? You could have more words, you were going to get better concentration of the moments, but just for guarantees, you needed just 3 words. Right? So you can have extremely short documents and still be able to learn this model with guarantees. And so that was a nice property of these moments. That's because we are only going up to third order moment, right? So it only suffices to have the information of co-occurrence of set of 3 words in the document. Okay? So, so this multi-view, the model, we can take it in different directions now, because we thought of like these topic models as multiple views. So I have multiple words in my document. These correspond to multiple views. And but we had this additional property of exchangeability, meaning that the conditional distribution of all these views was the same. Right? But we can generalize it further and instead have like a model where the this linear map for the different views may be different matrices. Right? So think of like different matrices AI. Right? So and here and they could possibly even be of different observed dimensions. Right? So you can think of like modeling in many scenarios. For instance, there may be like audio, video, and text data all talking about the same phenomenon. Right? I mean, you could think of it as on a web page, or they're talking about some, either some scientific concept or some speech, or of some rally. There can be so many scenarios, right, where you have diverse sources of information that talk about the same underlying state. And indeed, naive-based model is extremely popular in machine learning. And so what we can do is for this naive-based model, as long as I have these linear model for each of the views, I can in fact just slightly modify the moments and get the exact same form. I mean, if I didn't do the modification, what I would get for these second and third order moments would be asymmetric forms, because I have this conditional distribution given this hidden variable to be different for different views. Right? And this naive-based model, this hidden variable, we'll think of the case when typically it is just the categorical variable. Right? I mean, you could also do dirichlet. You could subtract out the extra terms as I described. But just for simplicity, think of this as just categorical now. So in this case, I mean, the only additional processing that I needed to do compared to the previous case is to make it symmetric. Because if I just thought about, say, this moments, right, there are like now different pairwise moments, because I take different sets of variables here, I get different pairwise moments, and similarly different triplet moments. But think of it as like, again, I'm doing like this linear transformation to symmetrize my moments. And in many cases, you may not even need to do that. There may be other ways to still use the tensor decomposition techniques directly on the asymmetric form. But just to make it consistent with the other models here, I've shown the symmetrized form. Any questions here? Yeah.
Is that Ross inverse?
Yeah. So this is like the pseudo-inverse. If so if D is equal to K, is just the inverse, but in general. Again, assuming that you have this full column rank, right? So that is like a prevalent assumption in all through all of these, yeah.
Can we go back to the NDM model?
Yeah.
For M2, is it the subtraction term is both expectation over X1, both of them?
I mean, it doesn't matter because it is exchangeable, so the statistics are the same for both the words. So the marginal statistic is just the same, right? Because and you can see that even from this conditional expectation, right? Because I mean I'm drawing these words, right? So in expectation, it's just nothing but A times the expectation of H, right? And for all the words, it's the same, so it doesn't matter. Okay, and so here, I mean, I did the symmetrization. I, transformed it to like the set of vectors for the third view. You could equivalently do it for any of the views. It doesn't matter, right? So this is just a simple, think of it as a symmetrization of my matrix and tensor. So hidden Markov models again are, ubiquitous, whole range of different applications. So here I have this series of hidden variables, right, that evolve. You can think of this maybe, usually people think of it as temporal evolution, right? So this is over time, you have this set of different hidden variables, and then you also generate these observed variables. And now, I've just shown here for 3 points, but you can do the same for, for how many ever points you have. And the unknown parameters here, this matrix O, which I'll call it the observation matrix, is looking at the conditional expectation of x given this hidden variable h. So again, I'll think of h as just categorical for simplicity, right? And I have the transition matrix for my hidden states, right? So the hidden state, right, just transitions to another one. And then the other specification I need is the initial distribution, right? So this one I think so yeah. So I have I think it should be for h. I think yeah. So I have these unknown parameters. So again, so how do I reduce it to this tensor method? So I can think of it as a 3-view model, right? Because if I think of this as my hidden variable of interest, right, this hidden variable just collapses. So think of it as there is an equivalent way to go from this hidden variable to this observed variable here, right? And similarly from this hidden variable to this observed variable x3 here. And to show that why this is true, I mean, I'm just looking at like the conditional expectation of all these observed variables given this middle hidden variable. I mean, they have all these linearity, and again, conditioned on this hidden variable h2, all these views are conditionally independent. So I can just reduce it to the multi-view model that I described in the previous slide. And and I want these, and you can think of them now as these effective matrices, right? So I have now these different matrices for these 3 views of how the hidden state transitions to the observed state. And again, I would need some non-degeneracy conditions that this observation matrix has full column rank. This transition matrix is invertible, and these, pi and t pi have these positive entries. So again, like this hidden Markov model as well, you can reduce it to this tensor form. Okay? And you can do this like over, now you can like have like pairwise moments and third order moments, and you can also now average it over this hidden Markov chain. So we see that even hidden Markov models can be reduced to the form that we're going to use. And the last one of these class of models, this is the ICA, or the independent component analysis. This is a classical model in signal processing in a variety of other areas, where the task is to unmix these sources, right? So typically think of like multiple people speaking in a meeting, and you'd like to unmix the individual speakers, right? So they're all talking simultaneously. How do I find this unmixing matrix? And the model for this is that my observation is a combination of these unknown sources. So these A1 through AK are now these vectors corresponding to these unknown sources, right? So these are the mixing of the unknown sources. And sorry, H1 through HK are the sources, and A1 through AK are these mixing, mixing vectors. Right, so I have these hidden sources, and I have a combination of them that I'm going to observe, and I also have this noise. And the noise, we'll think of it as Gaussian, and that's because we'll see that that's needed for the cumulants to work out. But if you see this model, you see that it's quite similar to the Gaussian mixture, right? In fact, it's exactly the same form for the Gaussian mixture. The only difference was this hidden variable h was just basis vectors, right? You were selecting one of the k components, so the hidden variable you assign them these basis vectors. But now I'm going to assume some general distribution for these hidden variables, but they are all independent. So these different coordinates of H are drawn independently from some distribution. Right? And these could be even different distributions. They just need to be independent. And it turns out that when you have this independence, there is this cumulant that has the form that we require. So here I showed the fourth order cumulant because if I have these sources being symmetric, meaning their odd moments are 0, then the third order moment has no information. Right? So typically then you think of the fourth order moment. On the other hand, if the distributions have skewness, then you could also look at the third order moment. And so this is the cumulant form because I'm taking this raw moment and I'm subtracting these, these second order terms in this case here. And so the assumption is this parameter, what I call kurtosis, is non-zero for all the sources. So this parameter is 0 if it was Gaussian. So you have to have the sources be non-Gaussian. In that case, you can uniquely identify these sources. Right? You can identify the mixing distribution, and you can identify the mixing matrix and the sources. So is that clear? So all these models, what we are seeing is that we can obtain moments which are multilinear forms of these set of unknown vectors. Right? So there are k vectors, a1 through ak, and I have multilinear forms of them. And that's why we see that they all reduce to this tensor decomposition problem that I introduced in the previous class. So now we'll even take this story further and look at graph-based data. I mean, so far we looked at this data, which was just data points in d dimensions. But now with graphs, I have these like pairwise relations. And even in these cases, we can incorporate latent variable models and use these tensor methods for learning. But before I go there, any more questions on the models I introduced? Yeah.
When you have those different views, the audio, video,
yeah.
Were you expecting words from the views, or you're working with the signal from the views?
Just the raw signal itself. As long as you have this conditional independence, right, that model, and the fact that, like some transformation of the signal, you have that linear form, then you can use this setup. And you could further, incorporate kernels. You could incorporate additional machinery if you wanted to model richer class. But all we need is this conditional independence that there's no direct relationship between the views, but only through this hidden variable. Okay? So now let's go to graph-based data. So as a motivation, and this is what I introduced yesterday, we can think of social networks, and here latent variables can correspond to these different groups that people belong to. Right? So these could be like, for instance, on Facebook, like the people that I went to college with, I went to high school with, like I have some hobbies and interests with, and so on. Right? So you can classify people into different groups, and I'd like to know like these by observing the social ties or these friendship connections on Facebook. Can I infer what are the groups that people belong to? Right? And so that's what is like the classical problem of community detection, and we'd like to be able to do that. And although I won't describe this recommender system here in detail, we'll see some experiments tomorrow using data from ELP. And it's in fact a very similar framework of probabilistic modeling as this social network setting. So here now think of it as a network where it's a bipartite graph. There are users on one side and products on the other. And the users tend to like certain products, right? So those are the edges in my bipartite graph. And the latent variables are what is the choices for different users, right? What do they tend to like? I mean, are they interested in books? Are they interested in games? So on. Like these are the interests of users. And similarly, products have various attributes or groupings, right? So what are the communities of users and products that lead to these connections in the bipartite graph? So it's very similar to the community setting, except that this is this bipartite model. So how do I model, now it's said that these are the latent variables. And my observed variables is this network. Right? So I have a random graph model where I have these hidden communities or groups that I'd like to recover. So how do I go about modeling this? So, we'll again take this viewpoint that, the users who are in, say, similar groups, right, will tend to connect. I mean, although that is not completely required, just think of that intuition for this example. So think of like every person in the network has some hidden set of memberships, right? So these are, say, for instance, the fraction of time they spend in different interests, right? So somebody is like spending almost all their time in computers, maybe a lot of people here, all right? There are others who are maybe spending more time hiking. So users have all these different interests, and think of this as like fractional interest into different communities. And users now meet in different contexts, right? So, here I'm meeting you in the context of machine learning school. So if we are talking about a machine learning topic, it's more likely we'll have a tie, right? We'll kind of make a connection. And so you can think of the same here in this example. These two people meet when they go to a dance. So there is a high likelihood of them forming a tie, right? On the other hand, if like they're at a random point of time, they're spending their time doing something different, right? One person is hiking and the other person is doing computers, then they may not form a tie. Right? So think of it as like for all these different interests, there are some unknown probability of being connected. Right? And on top of it, there are also like now people having multiple interests that are unknown. In fact, this is very similar to the topic model that I described. So there we had these multiple topics, right? And given these topics, you were drawing the words. So here we have multiple interests for every person, and given these interests, I'm drawing the connections or the edges in my graph. And we'll see, in fact, the connection is even deeper than that, and I'll come to that in a minute. So this is the intuition of how the model is generated. Let's now see the details, right? And this is not our model. This was a model that was, proposed by Iraldi et al. I mean, it's been since extended to a number of settings. It's been widely employed. So I'm going to again fix the notation, K is the number of communities, right? Because again, that's my dimensionality of my hidden space. And here the observed dimensionality is in fact n square because I have n square possible edges. So G is my adjacency matrix, which is a realization of my edges in the graph. For now, think of it as Bernoulli variables or unweighted graph, but this can very well be extended to weighted graphs as well. And so I'm going to again represent fractional memberships of the nodes into different communities. So I'm going to use the notation that for a node x, pi x is my membership vector. And again, I'm going to use the fact that these are fractional. So think of it as now I'm spending like some fraction of my time in these different communities, right? That's one interpretation of these fractional memberships. And now I'm going to again assume that these are drawn from the Dirichlet distribution. I mean, same as in the topic modeling. There, the topics were drawn from the Dirichlet distribution. Now here, the membership of nodes into different communities are drawn from Dirichlet distribution. But you can also see where the difference is, right? So in the topic modeling, in a particular document, I only had one draw of my Dirichlet distribution. So this was the proportions of that of those topics for the entire document. But here, for now, I have this graph, and for every node, I have a Dirichlet distribution draw. So I have like now my, in fact, hidden variables are these k-dimensional vectors, and there are n of them corresponding to n nodes. So I have to estimate a lot more here. But I also have more information because I have like n square kind of dimensionality observation, right? So it's, there are still a lot of differences from the topic modeling, but there are also similarities. So So this was in terms of like how these unknown community memberships are drawn, right? So my latent variables are these set of vectors pi x or pi u, right? The memberships of different nodes. So now this is the generative model. Given all these hidden variables, how am I generating my observed variables, which are the edges in my graph? So we're going to assume that all the edges are conditionally independent given these community memberships. So again, you can think of this kind of a hierarchical model as in the topic setting, right? So in topics, like given the proportions of topics in the document, the generation of all the words are conditionally independent. And here, it's like the set of edges are conditionally independent given the community memberships. And I'm going to use another assumption, which is now makes it a linear model of a very similar flavor to the previous class of models. So I'm going to assume that the probability that a particular edge is generated, right? So this is the edge between nodes I and j, conditioned on the certain configuration of community. So pi I and pi j are the set of memberships for node I and node j. So we'll assume that it has this bilinear form. So how can I interpret this form, right? So think of the special case if they were just pure communities. So meaning pi I and pi j were just basis vectors. So for instance, node I belonged to community 1, node j belonged to community 2. So in that case, what I'm doing is just querying this the element of this matrix P, which is the 1, 2 element, right, in the first row and second column. So think of it as that if these were just pure communities, right, just like every node just belonged to one community, this model, all it's saying is that there is some underlying probability for connectivity across different communities, right? So the connectivity of a node is only determined by its community. And so the probability of an edge is only determined by the community memberships of the two endpoints. And here what we are saying is if they are mixed membership, if the node belongs to now multiple communities, think of it as an average over all the possible, kind of the support of the memberships of the two vectors. Right? So that's why we think of it as like the model where I'm spending like some amount of time in this community 1, and even the node j is spending some amount of time in its set of communities. And this is kind of a combination of those memberships. Okay, and as I said, this matrix P, which is a k by k matrix, represents like the connectivity for pure communities, right? If the nodes were just purely in those communities, you'd have this probability of connection. But because now nodes can belong to multiple communities, you have this kind of an average form. Okay, any questions here? Right, so the model is, you can see, more involved than the topic model because I'm generating this Dirichlet draws for all the nodes which form the communities, and once I condition on those draws, I'm drawing the edges. And then I'm obtaining that these edges have this average probability. I mean, there is a minor difference from the work of Iraldi et al., but we'll see, in fact, for the moments it doesn't matter. So I won't kind of go into the detail. I mean, it's in this sense of how these edges are generated. So let's just visualize these the models. I think that always kind of picture tells a better story, right? So the case when the Dirichlet parameter is 0. Right, was the pure community model. So every node just belongs to one community. So same as in the topic case, so every document just had one topic. In this case, every node just has one community. So here, think of this as like now there is a blue community, right? So these are the set of nodes that belong to community 1, community 2, and so on. And here I've assumed that the connectivity is higher within the same community than outside. So you see that if I had this random draws, there is more likely that there are edges between nodes in the same community than nodes across different communities. So it's a nice block model. I mean, these are kind of nice clusters. So you can even visually see that you can say that, oh, this should be one community, this should be another community, and so on. But the picture gets more challenging as I have mixed memberships. So when I have nodes now, for instance, this Dirichlet parameter, I'm setting it to 1 in this case. I kind of have these nodes which now are in multiple communities, right? And I'm just using this RGB configuration to just, the color represents the membership into different communities. And you can see that, the nodes that are mostly in one community are like this tight cluster here, whereas the nodes that now belong to multiple communities have kind of these edges more, spread out. It's not a nice block as here. Right, so you can see that visually it should be harder to recognize these mixed communities. Right, and in fact there is a lot of work looking at learning these stochastic block models for the single community setting. Right, spectral clustering, so many different techniques are present for this one. But for mixed memberships, there are a lot fewer works, and in fact, we'll see that through the tensor method, we can now incorporate these mixed memberships or overlapping communities. So think of it as now there are these two communities, but they also overlap quite a bit. That's why there is not this nice block structure as in the pure community setting. Okay? And in fact, as I increase this concentration parameter, if you recall for the Dirichlet distribution, I had that my sparsity level would go up. Right? Meaning the node is likely to be in more communities as I increase this concentration parameter. And you can now see that, you can also see that in the coloring here, the nodes are now kind of in more communities than before, and it does become harder to tell apart what the communities are. So although I won't be talking about the complexity of learning as a function of this concentration parameter, I mean, we have in the paper, the details of how it depends on this concentration parameter. So indeed, the problem gets harder as I increase this concentration parameter, because the communities overlap more in that setting, and that's why the learning is more challenging. Okay, but although these graphs look very different, the unifying assumptions we are going to use is that I have these community membership draws, and given these community memberships, the edges are conditionally independent, right? And we'll see that because of this assumption, we can handle a range of different models with different levels of overlap amongst the communities. Yeah.
Especially with tangential, but has there been any generalization of this work to capture communities that have different intercluster and intracluster connectivity?
And in fact, we allow for that. So it can be any general matrix. So the matrix P you saw, which was the connectivity within cluster and outside cluster, can be any general matrix that has full rank. But I think the question you're asking is also that within the same community, can I have different connectivity? Is that the question you're asking?
The question was so in this model here, like the intercluster connectivity and the intracluster connectivity is the same for all clusters.
Yeah. I mean, you mean across different clusters? No, that doesn't need to be. That's what if you recall, we had this matrix P, right, which looked at the connectivity across all different communities. So these are k-square parameter. For every pair of different communities, there's some probability of being connected. And this can be any general matrix as long as we have it to be non-degenerate. So it is full rank. That's enough for our settings. But for so many other algorithms, it is true that they're much more restricted in the assumptions. And also just to point out, there can be extensions of this model where even within the same community, there's some degree distribution, and then there is this average connectivity. So there are possible ways to even make this model richer. But we can handle the most general case within this class of models. Okay, so this was the model. Now the question is, how do I think about moments of this distribution, right? So this is still a distribution because I have random graphs. So I have realizations of this graph, and then I want to learn the parameters, which is the memberships of the nodes into different communities, as well as how our different communities connect with one another, right? That matrix P, which represented the average probability of connectivity across communities. So yeah, so now what are the moments, right? So if I have a random graph model, I can think of the presence of different subgraphs as possible moments. So in a way, this is a much richer model because I have kind of these different combinatorics. I have different possible subgraphs I can think of that can give me different different kinds of information about this distribution. And I mean, in general, indeed, that is a very deep problem in combinatorics onto like even characterize the subgraph polytope. Like how do I characterize like the presence of different subgraphs in a given graph, right? But we won't be dealing with any of those hard problems. We'll just look at one particular subgraph, which is a star with 3 leaves. And we'll see in a minute how to come up with an estimate of these counts. And for our method, this is enough to learn, right? So I'm not saying there are other possible ways to learn, but for our method, this is the moment we're going to employ. This is the subgraph we're going to employ. So again, you see that in all the models that I described, there is a bit of an art as well, because I have to know how to pre-process the data to reduce the moments. And even here, this is more of a decision to obtain tractable moments. Yeah. So the moment that what we will count is we'll look at, we'll first just divide the graph into 4 sets, right? So partition the graph into 4 sets. And for theory, it can be just a random partition. In practice, maybe you'd like to find a cut across which there are large number of edges, right? Because you have more information. So just partition the graph here into 4 sets. And the statistic I'm going to compute is this, again, I use this M3 because it has a very similar relation to the moments we have been looking so far. But here, what I'm going to count is like for any given triplet of nodes. So this node here, A, B, and C, I'm going to ask how many common neighbors they have in the set X. Right? So think of it as like I'm counting these a presence of these 3 stars, but I'm just putting these nodes of the star in different sets for removing some dependency issues. And I'm averaging over the set of nodes here in X. Okay, so that is exactly this parameter, right? So now this is a tensor because I'm doing this count for every triplet of nodes in the sets A, B, and C. Right? So for a particular triplet here, A, B, and C, this is exactly the how many nodes X that have all these 3 edges present. Right? So G is my adjacency matrix. And I'm taking the average count here. And this is equivalent to this tensor notation. Because if you recall the notation that I described yesterday, this is nothing but, if I query for node A here, that is nothing but like and I'm querying for node B, in this vector and node C in this vector. Right? So this here, Gx capital A represents the set of all the edges from node X to this set A. Okay, so it's a vector. And similarly, this B and C. So now you can see that this is a 3rd order tensor. Because I'm just looking at how many common neighbors every possible set of triplets in these sets have across here in this other partition. Is that clear? So this is again a 3rd order tensor. The question is, what is this bias, right? Why am I computing this? How can I exploit the statistical constraints that I described? Right? So if you recall, we have this property that these edges are all conditionally independent given the community memberships. So how can I exploit it to ask that if I looked at the expected form of this moment, right, what is the form it has, right? I mean, this is just the empirical moment, but in expectation, what does it look like? So it turns out that, in fact, it reduces to the multiview model that I described before. So, yeah, so how do I think about this? So what are my random variables in this graphical model? So I'm going to look at the set of edges that go from this node X to this set A, right? So this neighborhood vector for node X going into set A, and similarly for set B and set C. So these are my three views, three observed views, and my hidden variable is the membership for node X, right? So what are the set of communities that node X belongs to, and in what proportions? And this is where the conditional independence, right, it's obvious. Because our assumption is that the set of edges here is conditionally independent of the set of edges that goes to the set B, conditioned on the community membership of X. Right? Because these sets A and B have no other nodes in common. They have no nodes in common, and these set of edges, right, are only dependent on the community membership of pi X, or this, variable pi X. Is that clear? So that's why we can reduce it to a multi-view model by partitioning these set of edges. And now I have the dimensionality of these vectors is, say, of order n, right, where n is the number of nodes. So I have now a high dimensional vector, right? If I just looked at a single edge, it's a scalar. But I'm taking now a set of edges together, so I have sufficiently high dimensional observations. Because the dimensionality of my hidden variable is now k, and I'd like to be able to estimate that. And again, we have this linearity assumption here. I mean, if you recall, we had this assumption of how the edges are generated given the community memberships. And by just modifying it slightly, we'll see that it's just a linear function of this memberships of node X. So that's why I have these matrices U, V, and W. These are, again, the linear maps of the community memberships to the set of edges, right? So in expectation, I have this form. Okay? So, yeah, so I mean, I should have, my earlier M3 was, so should have been a slightly different notation because that was only for the stochastic block model. For the general model with Dirichlet, for a general Dirichlet model, we'll again have to have these shift terms, right, as I had before. But think of the intuition that because I have this multi-view model and I have this hidden variable being Dirichlet, I can use the moment forms that I had before. Right? So essentially, I have to symmetrize it, and I have to subtract those some set of terms because it's this Dirichlet distribution. So don't worry about the details here. I can find it in the paper. But the idea is I'm going to symmetrize the different views here. I'm going to subtract out some terms because it's this Dirichlet, depending on the Dirichlet parameter. And then I can reduce it to the moments in expectation being like just this bilinear and trilinear forms. Okay? I mean, the community problem is much more involved because even after I obtain this, I should go back to obtaining the communities, right? But just for now, think of it as, I have these second order moments, which is looking at two stars, right? It is a star with two leaves, and I'm counting how many such stars are there where the head is in this set X, right? The top node is in this set X. And similarly, I'm looking at these trilinear forms, which is like looking for every triplet, how many these common neighbors they have. Right, so those are these counts here. I'm doing some symmetrization operations. I'm going to subtract out some terms. And in the end, the expectation has the same form as I had before. Right, so these are bilinear and trilinear forms of some unknown set of vectors. Okay, and this I did it conditional expectation fixing these communities because think of it as I'm averaging over this set X. So I'm only averaging over the memberships of this set X. So, so there are some subtle differences from the usual topic model. There's a kind of a much richer story with these community models. I'll refer you to the paper unless there are some specific questions I can answer now. But indeed, it's much more nuanced than the topic model. But you see the similarities that are shared here. Like the main, I think the takeaway message that I'd like to, for you to have from these community models is by partitioning the nodes and looking at set of edges across this partition, you can reduce it to multi-view models, right? So you can have that the hidden variable is just the community memberships, and the observed variables are the set of edges that go into these sets in the partition. So there is a way to exploit these conditional independence relationships in a way to reduce them to this multi-view model. And that is kind of the key point to obtaining this tensor form. But indeed, there are a lot more details, and I haven't even shown all of them. Okay, any questions in this part? Okay, so we'll move on. So yeah, so far we saw that for a range of different latent variable models, we can reduce the moments to a form which is bilinear and trilinear forms on this unknown set of vectors, right? And yesterday, you saw that we could then go about recovering these decomposition, and there was this notion of whitening where I was reducing it to an orthogonal form, and then we used the power method to recover the eigenvectors. But yesterday I didn't show any analysis on why this does what I claim it does, right? Why does it recover the decomposition? So today we'll take the optimization viewpoint. We'll look at like what is it optimizing first of all, and why the power method converges, where does it converge to, right? How does it work under perturbation? Kind of the entire set of analysis to show why this is a guaranteed method. So let's recall the basic tensor procedure from yesterday. So from now on we'll just have these pairs and triples moments, which is like looking at bilinear forms of these AIs and trilinear forms of these AIs, right? So we'll only work with this from now on. And the first step we saw was to do this whitening, where what I'm doing is implicitly I'm rotating, or rather doing a linear transformation of my set of unknown vectors to an orthogonal system. And we argued that we could find this transformation using SVD of the pairs moment. Okay, so I won't show the detail here, but it's just a simple function of the SVD. Right? And once I had this, what I did was I was changing this original tensor to this new tensor T, which is only in k dimensions, and also that it has an orthogonal form. Right? So we knew that the different components of this tensor were orthogonal to one another. And then we employed this power method to find these eigenvectors. And the intuition of the power method was that I start from any vector, I do a quadratic operation, I normalize it, and then I keep repeating it. And then the hope is it will converge, and once it has converged, I'm going to deflate, meaning I'm going to remove that component, and then I'm going to just do it again. Right? So this was the basic tensor method. Any questions here? So everybody is has an idea of this method from yesterday. Right? So now we'll just jump directly to this orthogonal tensor, because the power method analysis is the one which we want to go into the detail, right? We know that from matrix analysis the SVD works out, we have this whitened form and so on, so that's kind of easy. And we also know that once we obtain the orthogonal decomposition, we can go back to this d-dimensional space, because this W is an invertible transformation, under the assumption that we have full column rank of these AIs. Right? So we'll only be analyzing this power method from here on. Yeah, so this is the form we had. So lambda i's were the eigenvalues and vi's were the eigenvectors. Right? Under the assumption we have an orthogonal system. right? So, and the reason why they're orthogonal is because if I, input any of these vectors, say I input v1, right, and did this quadratic operation, meaning I contract the tensor along two of the modes, right? So if I contract the tensor along two of these dimensions, I get a vector back. And if it is the same vector as I input, then it's a fixed point of this operation. And this is the notion of eigenvectors for the tensor. Right? So we did this yesterday, I'm just recalling that. And that's why we employ this power method for finding the eigenvectors. Because the hope is even though I start from some, any initial point, I'm going to eventually converge to these fixed points. Right? So, these are all the questions we'd like to ask, right? Does it really converge? And where does it converge to? Right? We know that all these components here of the decomposition are eigenvectors. Right? What if there are other eigenvectors? Right? So can it converge to other points? Right? In fact, that is the most serious problem in all this non-convex optimization. Right? Where do I converge to? Right? So I don't know that. Because there are multiple local optima with their own basins of attraction. So depending on where I initialize, I could converge to different points. So we'll spend the majority of time on this aspect, but I'll finally just touch upon a little bit more on this performance under noise. Because in reality, I don't have an exact orthogonal tensor, right? This is the expected moments. But I only have empirical moments, meaning I have perturbation. So what is the performance under perturbation? And even here, the story is much more subtle than the matrix case. But all along, we'll be going through the matrix analysis, and I'll try to kind of compare and contrast these two settings. So hopefully that'll be helpful. Yeah, so just to recap here, right, first we'll just see for matrices, what do we have? And then we can go to tensors. So we know for symmetric matrices, we have the eigen decomposition. These eigenvectors are orthogonal to one another, right? And they are fixed points of this equation here, right? If I take m times v, it's just the same as, it's just again stays at v. The lambda is just the scaling, which is the eigenvalue. So just I'm writing it in this notation because this is the multilinear notation that I described yesterday. Meaning that I looked at, I'm taking the second mode of this tensor, right? You can always think of matrix as a tensor of two dimensions, right? And then, so these two are equivalent notations. So I just rewrote it to remind ourselves that notation. And so the very first question is, when is this eigen decomposition unique? Right? So when do I have this unique set of eigenvectors and eigenvalues? We all know that as long as these eigenvalues are distinct, I recover these unique vectors. Right? Otherwise, I only recover up to subspaces. So this is what I call the identifiability question, because you'll see again with tensors, the story is much more involved. Right? It's not as clear as this one here. And how to recover the eigenvectors, again, we have the matrix power method. Right? So again, I just wrote it in this notation. You'll see the parallel to the tensor case. Right? It's exactly the same concept. And what are the convergence properties we have in the matrix case? So we know that as long as these eigenvalues are distinct, right, we can recover all these eigenvectors. And as long as I have an initialization with a non-zero component at the top eigenvector, right? Meaning the eigenvector corresponding to the largest eigenvalue, it will converge to that point. Right? So in a way, like a lot of matrix, kind of properties are nice because you know that a random initialization would have this non-zero component along the top direction, and you know it will converge to that. So in a way, like even though this is, you'll see from an optimization viewpoint, this is a non-convex problem, right? I haven't yet introduced this optimization viewpoint. But the nice thing is, like some very clear convergence properties. In except for a set of measure 0, you have convergence to this top eigenvector. So, and perturbation analysis, we have this Wedins and Wales theorem, or this also kind of equivalently this Davis-Kahan, which says that if I have this perturbation matrix E, as long as the spectral norm of E, right, is less than the separation, right, the minimum separation, I'm good. I can still recover all the eigenvalues and eigenvectors up to some perturbation, right, of the same order as this spectral norm of E. Right, so the matrix perturbation analysis is very well developed. I mean, there are a lot of very nice results. So this is just a recap. Now let's see how to ask the same questions for tensors. Any questions here? So let's now see the story with tensors. Sorry, before that, let's see the optimization viewpoint. Okay, let's stay at matrices. So that was the just the power method and how to recover the eigenvectors. The point I want to stress is an optimization viewpoint, right? How can I think of finding these eigenvectors as an optimization problem? And I did introduce it in the beginning of first lecture. You can think of it as optimizing the Rayleigh quotient, right? So this Rayleigh quotient was this quadratic form, and I'd like to optimize it over all vectors with unit norm, right, or vectors on the sphere, right? So that is this problem here. So this Rayleigh quotient is like, this quadratic form of this nature here. So I think it's pretty easy to see that the global optimizer for this should be the top eigenvector, right? Because if I have, just this V to be the top eigenvector, I get lambda 1 as my answer, right, the top eigenvalue. And at any other point, it can only be lower, right? So this is the global optimum of this problem. And indeed, this is a non-convex problem because I have this norm constraint, right? So that's kind of obvious. Right, so I have a non-convex problem. I know what the global optimum is, but in general, there is no reason that I would be able to get to the global optimum, right? That's kind of the whole difficulty in solving non-convex problems. But it turns out, like for this matrix analysis, we can characterize the local optimizers, and we'll see why that relates to the guarantees of eigendecomposition, right? That relates to why we can do this eigendecomposition efficiently, and we'll see that in a minute. Okay, so to see what are the local optimizers, the first thing we'll do is just write down the Lagrangian. Because I have this norm constraint, I'm going to write down the Lagrangian incorporating that constraint. Right? So lambda is a Lagrange multiplier in this case. Right? So I've just written down the Lagrangian. Now I'm going to just take derivatives. Right? So I'm going to look at the first derivative, and I know that the stationary points where this first derivative vanishes are like the fixed points, right? So these are fixed points of this equation here. And these are exactly the eigenvectors, right? So the stationary points of this optimization are exactly the eigenvectors of my matrix, right? So this is by definition, right, where this vanishes. So all eigenvectors are stationary points of this optimization. And if I think of like the power method, you can think of it as a version of gradient ascent. I mean, I said ascent because I have a maximization problem here. Right? So that's because I'm like, so think of it as like gradient ascent with like infinite step size, right? Because I'm only I'm changing the vector by according to this map. Okay, so I'm doing this power method, but the question is like these first order derivatives only tell you the stationary points of optimization, right? In order to talk about local optimizers, I should go to the second order condition, right? So let's do the second derivative. So I have this form here, right? I mean, I just have this, just as a detail, I had this multiple 2 here because I have this symmetric form, right? So I have like twice that. And I no longer have that here, so I'm just carrying that over here. Okay, so I've just taken the second derivative here. Just to recall, what is the condition for a stationary point to be a local optimum? This is true for any constrained optimization problem, that if I take like the second derivative of the Lagrangian, and then I look at all directions W that is perpendicular to my vector V, right? So that is the stationary point, and if I look at all directions perpendicular to it, this quadratic form should be less than 0. So this is a general condition for any constrained optimization problem, right? So a general condition for the stationary point to be a local optimum. Okay, so we'll now just apply this condition to the matrix here, to the Rayleigh quotient optimization problem. Okay, and you can immediately, maybe not immediately, if you take the time, you can verify that in fact that only the top eigenvector is the local optimum. So in a way you can see that, because if if V is equal to V1, like the W's can only be perpendicular to that, right? And that means here in the second derivative, this lambda again would be actually the top eigenvalue, and everything else is less than that, so it will be negative. Okay, but you can also verify that there are no other local optimum. And in fact, the other eigenvectors, which are stationary points of this optimization, are only saddle points. Meaning that if you just, there is some direction where you would move away from that, right? So as long as you don't initialize directly on those eigenvectors, right, as long as there's some component away from that, you would move away from there, from those points, right? So this is again, the standard notion of saddle points in optimization. Okay, so that's the result here, that because I have this power method as gradient ascent, right? As long as I initialize with some component in the top direction, I'm going to converge to the top eigenvector. Okay, so this is a very clean optimization viewpoint of matrix power method, right? Why it converges to the top eigenvector. Okay, and we'll see that in fact there is a very there is an analogous tensor story, but a much more involved one at that. But I want you to be clear. Any questions here would be, I think, better, because once we go to the tensor case, it's much more complicated. Yeah.
Is the Lagrangian function convex?
I mean, though you take the Lagrangian, there's still this constraint, right? So this optimization is non-convex. Right? So it's not a convex problem. But because of this nice property that the global optimum and local optimum are the same thing, right? And all the other stationary points are just saddle points, we can solve this optimization. So that's kind of the nice thing about this matrix case, right? So it's much like this, in fact, kind of a best case scenario for a non-convex problem. Right? Even though it's non-convex, I have the local and global optimum to be the same thing. I just have like these other saddle points. Right? So as long as I don't initialize directly on those saddle points, I'm good. Okay? So that's the matrix story. So now let's go to the tensor case. Yeah.
But isn't Lagrangian convex or concave in this case by definition?
But you also want to enforce the constraint, right? So ultimately you want to obtain a solution which is normalized. I just wrote down the Lagrangian to ask what are the stationary points of this optimization problem. And then I'm writing this, and this is the condition for point to be local optimum for the constrained optimization. So I'm going to take the derivatives of the Lagrangian, and I'm going to verify these conditions to check what the local optima are. So what are the stationary points? What are the local optima? Yeah. Okay. So let's now go to the tensor case. We know that the general decomposition of tensors is NP-hard, but we are now limiting only to the orthogonal decomposition, right? So there is some hope here. The general one is much harder. So let's first, so this is just kind of saying that the general case is hard, let's do the orthogonal case. And so as we saw till now, the components of the decomposition are eigenvectors, right? Meaning that if I started at any of these any of these vectors in the decomposition, right? Any of these VIs, right? They are eigenvectors because I take this quadratic operation, I still recover just the VIs themselves. But the bad news is there can be other eigenvectors. So already you see the divergence from the matrix case. In the matrix case, I had a very similar decomposition, right? And the only eigenvectors were part of that decomposition. There were no other eigenvectors. But here, we know that there can be like these other eigenvectors that are, so that can exist here. I mean, this is just one example. If I had like all these eigenvalues to be 1, I can have this scenario. And even if they're not equal, you can still have it, but this is just an example I showed. So this is already bad news because not only are these components eigenvectors, there can be a whole lot of other eigenvectors. In fact, in general, there can be exponential number of such eigenvectors. So, because our whole hope was we would just start by this power method, right? We would do this power method, it would go to one of these eigenvectors. That was the hope. But then there are so many other eigenvectors that don't give me this decomposition, right? That are not part of this decomposition. So how do I handle this setting? And so let's now again do the how to avoid like these spurious solutions, right? I don't want eigenvectors that are not part of the decomposition. So in order to say that I can recover this decomposition with guarantees, I should not go to a spurious point. Because in that case, I don't know how to distinguish what is the real point and what is spurious. So let's again do the optimization exercise. So it's very, it's completely analogous to the matrix case. So instead of the quadratic form, now I have the cubic form for optimization. Right, so this is analogous to Rayleigh quotient form for tensors. Right, so this is the the cubic form here, and I still have the constraint that I want to optimize this cubic form over all vectors with norm 1. Right, so it's very analogous to the matrix case. So I have the Lagrangian. I do the first derivative. I have the I think I needed like a factor here. Sorry, there should have been like I think a 3/2 here. So then that would have been, and that's anyway like that multiple does not affect anything because that's just a Lagrangian factor. But doing that factor, I would have just directly had the eigenvalue here. So there is a typo here, but it's a minor one. So if I fix that like factor here, I would get this as the first derivative. Right, and this is now just where this derivative vanishes. It's exactly the definition of my eigenvectors, right? Because what I'm saying is I'm doing this quadratic operation. I'm still, staying at the same point. So again, it's analogous to the matrix case. The stationary points of this optimization are the eigenvectors. By definition, they are the eigenvectors. So again, you can think of this power method as doing gradient ascent for this optimization. Right? So it's the same analogy as before. But now, in order to ask what are the local optimizers, I have to do the second derivative. Okay? And it's exactly the same optimality condition. Right? This is the general condition for any constrained optimization. And if you were to now verify this condition, you can check this. It turns out that the only local optima are just these VIs, meaning they are the components of my decomposition, right? So sorry. This was this decomposition. So only the components of my decomposition are the local optima. So we saw that there could be other eigenvectors other than the decomposition, right? So other than the components of the decomposition, there can be other eigenvectors. But luckily, they turn out to be saddle points. So, so that's why you can still provide guarantees for the tensor method, because the only local optimizers are only the components of this decomposition that I have. Okay, I mean, it is more involved than matrices, because there in matrix only the top eigenvector was the was the only local optimum. But now I have multiple local optima, but thankfully there is nothing spurious, right? So these are all the components of the tensor, and I want to recover all these components. So that's why we are able to give guarantees. That is kind of almost the main property that's needed. And in general, for general non-convex problems, it's not true, right? We have all kinds of spurious solutions. That's why we cannot provide guarantees. But for this orthogonal tensor, we have a nice property that the local optima are exactly what I require. And that's why we can turn this into a guaranteed method. Yeah, so that's the nice property that because of this, in fact, just gradient ascent, which is this power method, will go to one of these local optima. Okay, any questions here? Yeah.
The eigenvalues of the third order tensor, are they always positive?
So without loss of generality, you can make them positive, because if it is negative, you can just kind of flip the sign of the v's, right, of the eigenvector. So you can just instead of v, you have a negative v. So by convention, you can just make it positive. For an odd order tensor, you can do that.
All eigenvalues?
Yeah, by convention, you can assume that. You can just make it the convention, because if it's not that, you just flip the sign of the eigenvector. But it's an odd order, right? So that's why it'll flip this sign. Because it's v tensor, v tensor, v. So if you make it minus v, you get a negative sign. Okay? So, yeah, so that was the property. That is, in fact, the main property why we can provide guarantees for tensors. So now I'm going to ask about the convergence rate, right? Like how we know that the power method converges to one of the local optima. What is the rate of convergence? If I start at an initialization, at what rate do I converge to the eigenvectors, right? And then after that, we're going to look at perturbation analysis. Under noise, what can I see? So those are the remaining points. Yeah, so for matrices, again, to recall, we have a linear convergence assuming an eigengap, right? And in fact, this rate of convergence depends on this ratio between the second and the first eigenvalue, right? So this is just saying that if I start with an initialization v, after some t iterations, you kind of have this buildup of correlation towards the top direction at this rate, right? So this is, I'm just just recapping the matrix setting. So it turns out that the tensor's case, where you converge depends on where you initialize, right? So in the matrix case, all we wanted was that initially I needed some amount of correlation with the top one, right? So there should be some non-zero component in the top direction, and that's enough for me to converge. But here, I'm going to now converge to a vector v, which has this maximum, which maximizes the product of the eigenvalue times the correlation along that direction. So the Ci is the amount of correlation along this direction Vi. Right? So these Vi's are the different local optima. So think of it as this is now an optimization. There are multiple different local optima with their own basin of attraction. So as long as I have and that basin of attraction is characterized by the product of the eigenvalue times the correlation along the direction. Okay, so I'm going to converge to a component that maximizes this. Okay, and this is just the power method, which is saying that it's a quadratic operation, right? So if I started with initialization with correlation Ci along each direction, I'm going to have this change into lambda I times Ci square, right? So I have this kind of a change in every iteration. And you can argue that in t iterations, in fact, I can have a quadratic rate of convergence to the eigenvector that maximizes this product. So, don't worry too much about the exact form, but, think about this here. That's why this is quadratic rate of convergence, because in t iterations, this shrinks as 2 to the t. Right? So that's why we have kind of a much faster convergence than the matrix case. Right? In matrix, it was just linear. Now it's quadratic, because the intuition is each time, like think of it as like Ci was really high along one of the direction. And for simplicity, just take all the eigenvalues to be the same. So I have equal eigenvalues, and say one of the C1 was very high compared to everything else. So what I'm doing is in the next iteration, I'm squaring it, right? So I'm even like kind of magnifying my already large direction by even more. So that's why I'm able to converge much faster, right? Whereas in the matrix case, I wasn't squaring, it's just Ci. Right? So that's kind of the only difference between the matrix and the tensor power method. But because of this quadratic operation, I even have faster convergence. Okay? So just to kind of put them side by side, we saw that for matrix power method, in order for convergence, we needed this eigengap. Right? Whereas for this tensor power method, for convergence, I need a gap between the largest and the second largest product of the eigenvalues times the correlation. Right? I mean, again, you saw that here, if these two were exactly equal, I would not have this convergence. So I need a gap between the top one and the second one. Right? There should be like kind of a significant advantage to one of the directions versus the others. Only then I would go to that local optimum. Otherwise, I would get stuck at a saddle point, right, if that wasn't the case. So yeah, I have to ensure this gap. And if I have that gap, then I would converge to that corresponding top quantity, like the eigenvector that maximizes this product. So you can immediately see that there is also an advantage of having tensors compared to matrices. In matrices, if these eigenvalues are not distinct, I cannot distinguish the components, right? I only get this subspace. But in the tensor case, even though the lambdas may be all equal, right? They may be just exactly the same, because as long as I initialize with different correlations to different directions, I'm good. I can recover these eigenvectors. So for the tensor, I can have these eigenvalues be exactly the same, and I can recover the components. So that's kind of also the advantage of having tensors. And in fact, going back to the problem of like the moments, if I had like, say, Gaussian mixtures with just equal weights, right? So if the equal probabilities, in that case, you would just get these equal eigenvalues. And we cannot, if it were the case like matrices, then that would not be good because we can't solve the uniform setting. Right? But that's thankfully not the case. With tensors, as long as I have good initialization, I can even handle equal eigenvalues. Okay, so in the matrix, we saw that as long as I initialized with a component in the top direction, I always converge to the top one. But here, I have this convergence to any one of these local optima, which are these components. And we saw that the tensor is even faster convergence. It's quadratic convergence compared to just linear convergence for matrices. Okay, so any questions here comparing the two settings? Yeah.
When you initialize eigenvector in tensor power iteration, how do you know which is the direction for the largest eigenvector?
I mean, you don't, right? I mean, this is the analysis. So we are saying as long as you initialize with different correlations, you're good. You would converge to one of them.
So basically...
And you just keep reinitializing. So you randomly reinitialize to different values, you would get different quantities. Or alternatively, in the orthogonal case, you can just deflate it. You initialize, you get an eigenvector, you subtract it out. Then it's like, there's very little, I mean, in fact, in the noiseless case, there is no signal along that direction, right? So then you initialize the orthogonal to that direction, right? So then you would get the other one, and so on. Okay? So you can see that there are a lot of shared similarities, but also very important differences between the two. So the perturbation analysis, it's in the paper. I won't go into details. In fact, this is much more subtle than the matrix case. So in the matrix case, we have this general Wales and Wedin's theorem that doesn't depend on the algorithm, right? So for any algorithm, no matter how you recover the eigenvectors or eigenvalues, you have these properties. But here, our perturbation is only limited to the power method. And in fact, in general, the perturbation is more subtle for tensors, because with the, and in fact for any general non-convex problem, right? Because if I have a perturbation, I could totally change my landscape. So I could create all kinds of new local optima, right? I could just change the configuration completely. So in that case, right, I may just get, although the noiseless case I had only good local optima, I could end up with all kinds of bad local optima. Right? So the perturbation is much more tricky in the tensor case. So, but we can give guarantees, but they're much more restrictive. Like the amount of noise we can handle is much less than what we could in the matrix case. Again, because of this kind of concern that I could just completely change the landscape if I had, just too much amount of noise. And there are some very sophisticated techniques. Very recent paper that came out that looked at sum of squares, Lasserre hierarchy techniques that can handle kind of the amount of noise to be as large as the signal. But those are quasi polynomial time methods, and so I can talk offline on details about that. But for this power method, you can't have too much noise. And so this noise here, again, you can think of a spectral norm of the tensor, the error tensor E here, which has to satisfy kind of a condition that depends on the minimum eigenvalue divided by k, right? So there's this additional aspect of k here, right? Whereas in the matrix case, as long as your noise is less than the minimum eigenvalue, you're fine, right? You would recover them. And of course, also the gap, right? I'm assuming you have enough gap. But here you need a more restrictive condition. And we also need n is the number of iterations for the power method. So we saw in the noiseless case it was quadratic convergence, meaning there was only log-log term. But because there's noise, there's also a linear phase because of the noise. But it's still fine. I mean, this is still in practice. We saw yesterday in that sample code and also in all our experiments, it's extremely fast convergence for the power method. But this is the theory that says that it's linear. And then we see that with polynomial number of restarts, meaning I randomly initialize and I take polynomial such number of initializations. The exact polynomial is given in the paper. And turns out that it's quite a small order polynomial, especially for this orthogonal case. And in that case, what we show is that we would recover the eigenvector and the eigenvalue corresponding to the top one, right? Corresponding to the one that maximizes this product with bounded error, right? So the same error as the noise norm. And then you can deflate and you can kind of recover one by one all of them. So this is the perturbation analysis, so you can think of it as a version of Wales and Wedin's theorem for tensors.
And so for the power method, worst case you would need k restarts to recover all the power.
I mean, it's more than k. It's k to the, I think, 1 point something. I think, let's say k square. And that's why we need is because think of it in the noiseless case, right? I just needed a gap between the top one with the second one. But now I need this gap to be sufficiently large compared to the noise. So that's why I need more restarts. Just one random initialization may not work out. And that's why I meant that this is some polynomial. Okay, so, and in fact, the deflation analysis is quite delicate for this tensor case because I have this, if I did it naively, I would have a big buildup of errors from one to the next step, right? And I want to avoid it by arguing that because I'm going to find an eigenvector that's orthogonal to the recovered ones, right? Almost orthogonal right, then I can control the error, right? So because of this almost orthogonality, I can also maintain the same level of error in all steps of deflation. And and again, I won't go into the details. This perturbation analysis, I can convert it into a sample complexity result, because I know my empirical tensor would have a certain perturbation, right? And for different models, it is different, but I can still analyze what that level of perturbation is, and then I can convert it into a sample complexity. And it turns out for all the models that I described, you need only polynomial number of samples for recovery. And I'll just maybe show one or two results where we even know what that polynomial is, and it's in fact very tight. But any questions here? So in the last remaining minutes, I want to just kind of motivate kind of where it's heading next, right? After like all these, we saw these tensor methods have guarantees in the case where I have full column rank for my unknown set of vectors. These are the mean vectors for Gaussian mixtures, or these are the topic vectors in the topic model, and so on. So this means that I needed to have the k, which is the dimensionality of my latent space, to be at most the dimensionality of my observed space, right? So k was less than d. But in many models, that's not the case, right? If you had like one-dimensional Gaussian, right, and many, many components, that is not true, right? And you could have like so many other settings where overcomplete models, which is the case where k is bigger than d, is kind of, has a much richer modeling power compared to these undercomplete models. So are tensor methods applicable there, right? So what is the story beyond? And just in some of our very recent work, so this is with Rong, who's a postdoc at Microsoft Research, and my student Majid, we've looked at these overcomplete settings, and we can still provide guarantees, right? But we know that the general decomposition problem is hard. So how we can kind of circumvent that is to impose some natural conditions. So we're going to assume that these components are incoherent with one another. So we know that we can't have exact orthogonality because we have more components than the dimensionality. But we know that we can have approximate orthogonality for a very large number of vectors. Right? So in fact, if you randomly drew vectors from, say, with bounded norm, right, with norm 1, like random vectors from the sphere, you'd in fact have them to be very low correlation. And the intuition is, again, where these incoherent representations, you could think of them also in a modeling framework. This is natural. Because you have your data, you'd like to fit it to components that are not too redundant, right? So you'd like them to be as incoherent as possible. And that's where, this framework, you can think of it as also like learning incoherent representations. So it turns out that we can learn these decompositions up to like when the number of components can be polynomially larger than the dimension, right? The rank of the tensor is polynomially larger than the dimension, right? Whereas in a matrix, the rank is at most the dimension. So again, you see the power of tensors, that although the analysis is much more tricky, it's also fruitful because we can learn a lot more with tensors. Right? So we can handle components be polynomially like up to d to the 1.5 with third order tensor. And in fact, for a general pth order tensor, up to d to the p by 2. So we can, as long as we have more and more components, we just have to go to higher order moments. And this is saying what is the order of the moment to go up to. Right? So, I'm definitely not providing the details here. There is some kind of analysis of like local convergence, meaning if I initialized close to one of these, components, where would I converge, right? And how I can analyze this local convergence. The other is the global convergence, and there kind of the story is a bit more unsatisfying because currently we still don't have a polynomial time. We need like a super polynomial time number of initializations. But in practice, we find that, in fact, you don't need that many initializations. Kind of, again, the intuition is these initializations are needed so that you land in the right basin of attraction to one of these points. And yeah, so the story is much more involved when you have these overcomplete case. But with tensors, there's the hope we can still take this story further. And the other aspect of the work that we've recently done is the sample complexity analysis. So it turns out that you by doing like some novel concentration bounds on by doing covering arguments directly on the tensor, you can get tight sample complexity bounds. So the one I described previously, I said it's polynomial, right? And for some cases, it's already good enough because many algorithms have exponential sample complexity, and that's terrible. So being polynomial is the first step. But then we want to ask what is this polynomial, right? How low of an order is it? And in the very recent work, in fact, we are about to post it on arXiv. We show that for a range of different models, we can get tight sample complexity bounds. So just as a flavor of result, for these Gaussian mixtures that I described, in fact, we just need like order k number of samples, where k is the number of components, right? This is the minimax rate. So you only need like the number of samples to be just k. And if I have like polynomially many components, I need a bit of supervision. So I do need some amount of labeled samples. But in the regime when the norm of the noise is the same as the signal, in fact, this has to be just polylogarithmic number of labeled samples. So in a way, because we are going to this overcomplete case where we have a lot of components, I do need some labeled samples. So it's semi-supervised compared to unsupervised. But the amount of supervision is still very small. It's just polylogarithmic number of samples that I require. And even the number of unlabeled samples to form my tensor is also tight. I only need like the number of samples to be order k, which is where k is the number of components, with some polylogarithmic factors. I've ignored the polylogs here. And so that's what we show, that with tensors, you can also learn highly overcomplete mixtures. Right? So you're able to find the decomposition of a tensor where the rank is polynomially larger than the dimension, but you're able to do it with a small amount of supervision. And that too, you can do it with very tight sample complexity results. Okay? I mean, you can also do the unsupervised case. As I said, the number of initializations is kind of growing exponentially in like the k by d ratio. So I won't talk about that here. So you can also get good guarantees for unsupervised, but to me, it's still unsatisfactory. I think there are still kind of questions on whether we can improve it further. Okay, so with tensors, we can do overcomplete settings as well. So this is kind of, I think, the exciting new work beyond what I described in terms of orthogonal tensor decomposition. And just to wrap up, there is also, you can think of like this dictionary learning framework, which is another form of overcomplete models. Because, I'm out of time, I won't give any more details, but just think of it as like each sample is a sparse combination of unknown dictionary elements. So in the compressed sensing, I know this dictionary, I just need to, recover these sparse coefficients, right? But in this challenging case, I don't know either the dictionary or the coefficients, and I have to recover both of them. And we had a work in Colt where we were able to, again, recover both the dictionary and the coefficients under incoherence. And in the most recent work, in fact, we've shown that even these tensor decomposition techniques can be applied for this dictionary learning problem. So in a number of different applications beyond what I already described, these tensor methods can be very applicable. So this is just like just a slide showing that if we had a method with guarantees and that could recover like the basis functions on this simple MNIST data. So although this was kind of a method with theoretical guarantees, even in practice it had fairly good performance. So I just wanted to make that point. Yeah. So in conclusion, we saw that there is a variety of different latent variable models for which we can express the moments as a set of equations that can be solved tractably using the tensor method. Right? So the tensor method used some simple SVD operations to convert it to an orthogonal form, And then we saw how the power method can recover the components. And today I talked about this optimization viewpoint, where we can think of recovery of these components as being local optimizers of this Rayleigh quotient form, right, for tensors. And we see that the perturbation analysis is much more delicate for tensors, as well as these, kind of issue of restarts. You have to kind of restart many times to go to one of the components when there is noise. So the perturbation analysis is much more involved. And finally, I just gave you a brief flavor of like this, I think, a very exciting set of problems, open problems, on how we can handle overcomplete tensors. How does the landscape of my optimization change when it's overcomplete? How can I use a bit of supervision to still obtain guarantees, right? How I can learn these overcomplete models for feature learning in a variety of different tasks. All right. And tomorrow I'll be talking about the precise implementation details, like what are the issues we run into when in practice we have to scale up these methods. How does the performance compare to like EM or variational base, right? What are the different kinds of data we can look at? Thank you.